Hello everyone, this video lecture is on pipes and filters, the second pattern from architectural patterns. So in this video lecture, we'll be studying what is pipes and filters and what it will be used for. See in this, the pipes and filters provide a structure for systems that process a stream of data. So it's usually used for those systems where we need to process a stream of data, and here the filter component implements one step of the process, that is nothing but the filter component usually does the processing steps, and the pipe carry data between the adjacent filters. Somewhat it will be like to show you, it will be like there will be some input device which inputs either file or any other input from another application. So there will be a filter there will be a filter which takes the input and does the processing or a computational task, and this pipe acts as a mode of transferring the data to another filter. Again it will do a task which is being taken from the filter one. Again this process will continue until it is passed to some other output device. So this gives us some conceptual view of how pipes and filter will be look like. Okay, so this how it provides a structure for to process a stream of data, and there will be two main components, that is filter component which does the computation task, and the other is the pipe component which does the task of delivering the data from one filter to another filter. And the other benefit is that we can recombine the filters, which allows us to build families of related systems. In the sense, we can recombine the filter, we can reconfigure them, we can add more filters, we can remove some filters. To usually it can use to another similar systems. The other question that comes to mind is how we are implementing sequence of transformation so that we can combine and reuse them independently. The next thing before to forces we have to look into the is that the context. So here the context is the situation which is giving rise to a problem is we want to process data streams. So the problem here is we want to build a system that must process and transform a data of input stream. So implementing such a system as a single component actually it will not be feasible. Suppose I want to transfer a data stream, and if I want to implement it as a monolithic structure, it is not actually a good idea for me. So what I'll be doing, I'll be again breaking into different subtasks. What I can say, I will be decomposing the entire monolithic structure. So there are different forces involved in building this forces involved for these pipes and filters. Let us see few of the forces. So the first thing is that here the processing of data elements can be broken down into sequence of individual transformation. So what we are doing here the processing of data elements can be broken down into sequence of individual transformations. So that can broken down into different subtasks. Hence, the smaller processing steps are easier to reuse and in a different context than larger components. So what happens whenever I break into individual sequence of subtasks? So this smaller steps are easy to implement and reuse. So, and the other thing we have to, I need to keep in mind that non-adjacent processing steps do not share information. So only here the adjacent filters will be sharing the information, but the non-adjacent processing steps, that is non-adjacent filters, will not be communicating with each other. And the different can be the sources of input data can be different. It can be a live sensor data, it can be a data file, it can be output from another application. So data can be anything, it can be of uniform format or it can be of different format. The next thing we are going to say is the solution of how we'll be doing this. So what we are doing, we are dividing the task into several sequential processing steps, right? As we have already seen in the forces. So what will be doing, we are dividing the task into different processing steps connected by a data flow. Output of a step is input to the next. So we can make from the figure that so you can make from the figure that how the first input device will be providing the data to the filter, and how that data from whatever processed data from filter 1 output of this filter 1 will be the input to the another filter 2. Likewise, the data they will be it will be processing sequentially based on situation to situation, that how many filters will be there. So output of a step is will be input to the next. Each processing step is implemented by a filter component. So what exactly the filter component is doing? The filter component is performing the computation. A filter consumes and delivers data incrementally to achieve low latency and enable real parallel processing. So while we have to keep two important things in mind is it helps provides us low latency, and it gives us uh, real parallel processing. So what happens whenever this filter, the added advantage of the filter is it can receive the data incrementally. So what we mean by this, so whenever data stream is being inputting delivered by an input device or some source, right? The filter will not wait for the entire message to come. So as and when the some of the data packets are passed to filter 1, it will start processing the data instantaneously, which will help us to achieve the low latency. And through this, even the real-time parallel processing can be done, because the filters can be having their own methods of control. Just we'll see what various different types of filters that are possible. So here we are dividing the application task into several self-contained data processing steps. So these are different data processing steps. These filters are nothing but these are data processing steps, and connect these steps to a data processing pipeline via intermediate buffers. So what I mean by here is this intermediate pipes will be having these buffers. So here the buffer can be a bounded buffer and unbounded buffer. It depends from application to application. But these pipes will be having a buffer, and they provide synchronization when there is a transfer of data from filter 1 to filter 2. So in between two filters, what we will be having? We will be having one pipe. The next thing is input to the system is a data source such as a file. As we have seen, the input to a system can be any kind of data. It can be a file, it can be data from another device, and output flows into data sink. So the input thing over here is a data source. Input will be a data source, and output will be a to a data sink. So if this data source acts as some input device, and data sink acts as some output device, and input filters and output are connected by what we have already seen through intermediate component, that is pipes, and these pipes will be having their own buffers, so which implement the data flow between the steps. So the sequence of filters and pipes combined is called what we call as a processing pipeline. Here, the filter are processing units of the pipeline. So as I said, the filter will be doing the task of computation. So let us highlight few of the tasks done by filter. So the filter can do the task of conversion. Suppose it can convert the data format from one format to the another format. These are explicit specializations what we can add to a filter. Data filter can even do the task of enrichment. In the enrichment, it can add some information to the incoming message. And even the filter can do the filtering job. It's nothing but discarding some of the messages which are really not needed and which match to a specific criteria. The filters are processing units of the pipeline. So it provides a stream to stream transformation. Yes, as as most of the filters can be stateless. They do not have any state information in them. They will not be having memory, and they will not be having the information regarding what happened in previous steps. So these stateless filters are very easy to implement and compared to the filter which maintains state information and which can be expensive as well. So these filters make use of little local context. So they will not be into much of the what the exact context of the streams, and they'll not preserve they'll preserve no state between the instantaneous. Actually, such no stateless filters are very easy to implement and they give actually the high performance. But when there is no state information, error handling will become difficult as there is no record of the previous transactions, whatever has been happened. But depending upon the situation, we may go for implementing stateful filter or a stateless filter. So how can be this structure of this pipes and the filters? See, in this case, the pipes and filters, the pipes and filters. Just a sec. When we speak about the structure of pipes and filters, there can be two types of filters. They can be an active filter and a passive filter. So what this passive filter is about? See, when this passive filter is activated only when it is called. So whenever the functions like so in this passive filter, whenever the passive filter is activated, it reads a single message from its pipeline and processes it and then writes to the result to the output. So in this case, a passive filter will be sleeping for most of the time. So whenever that is called, it will read the data from the previous pipeline. It processes and again it passes to the next filter. So there are two types of passive filter: the data-driven filter and a demand-driven filter. So what usually happens in a data-driven filter? It is also called as a push filter. It is activated when another filter writes data in its pipe. So what happens? The other filter, when it writes the data to its pipe, so this push filter will be activated. And the other is demand driven filter. It is activated when another filter attempts to read data from its empty output pipe. So what happens? Whenever this let us see with the diagram. This when if you consider this pipe to be a passive filter, so it will not be having its own thread of control. So this filter will be becomes active whenever it is called by the other pipes or other pipes or filter. Whenever what they do, the other pipes filter, they initiate a pull of data from this filter, right? And whenever it is called, it may initiate a push of data to these pipes. So when the push and pipe functions and procedures are being called, this filter becomes active. So that's what we mean by a passive filter. So this is what we call it as data driven filter and demand driven filter. That is nothing but a push and a pull type of model. A pipe transfers data from data source to a data sink, right? The main task of a pipe is to transfer the data. So pipe will not do any kind of computation or processing. The processing job is done by filter. The role of pipe is to transfer the data, to have a buffer. As we can see here, the pipes can have a bounded buffer and unbounded buffer. It can be limit or limitless buffers. It depends on from application to application what specifications we are having. And pipes can be between two threads of a single process. Yes, definitely there can be a pipes between two threads of a single process, and one of the example is of the Java IO streams. And even pipes can be between two processes on a single host computer. Yes, even this can be possible. There can be pipes between two processes on a single computer. One of the best example we can give is a Unix named pipes. And the third type we will see is pipes can be between two processes in a distributed system. When there are pipes between two processes which are located in two different pieces in a distributed environment, even pipes can exist between them as well. So in this, the stream content is usually limited to raw bytes. So as the pipes are in a distributed environment, the stream content will be usually between the will be having some raw bytes of data, and they will be having higher level of abstractions which will be making use of some strict protocols. Next, we see the concept of data pulling and data pushing. As we have seen in before slides, right? Data pull and push procedures or function calls are activated whenever they are called. So, what is the force that makes this data flow? There can be four choices. There can be push pull combination or passive combination. So whenever there's a push, data source pushes data in a downstream. You can imagine whenever there is a push, definite from one filter, that it pushes to a another filter. And whenever there is a pull, what it does, it takes data from filter one and it will be passed to filter two. You can imagine how this push pull model is working. And there can be even push-pull combination, right? A filter is actively pulling data from a stream, performing computations and pushing it to the downstream. So it can be a type of an active filter, right, where it performing both push and pull. And when we speak about passive, they don't either act, do either of these things. They act as just like a destination or a source. Let us see with a few of the scenarios here. The first scenario here is a push pipeline with an active source. The first scenario will be seen with an data source with a push, having a push concept. So in this scenario, what is happening here is, here this control is initiated by this data source. So what happens, it writes to the filter 1, right? And in this filter 1 there will be some computation which will be carried out. After that it will be pushed, the data will be written to the filter 2. Again there will be some computation performed. Again it will be returned to the data sinks. Data sink, it is nothing but the destination. So what we have to keep in mind here is, in this approach we are having an data source which is making use of a push. So the control is initiated by this. So it will write the data, computation is done, again this will write the data, again on push it to the another filter to, computation will be done, and again it will be transferred to the final destination. So this is one of the simple approach we can see. Again there can be a bit variant to this. Here a pull pipeline with an active sink. So here, in previous diagram we are seeing the source was active and it was implementing the push mode. But here the data sink is active, and definitely the data sink should use a pull model, because if the data sink means it is the final distillation, it should take the data from the last filter. So in this scenario, let us see the working. So in this scenario, the data pool will initiate the control. This sequence diagram is giving the controls of this various objects which have been taking place. So this will initiate the control, and um, the data will be this. The filter one will pull the data from here, and as this is a destination and there will be no data in this we have to remember, it is a data sink and it is a filter. So what the filter is doing, it is trying to read the data from the data sinks, as the data sink will be empty. Again uh, filter 2 will initiate the data here, and again it will be empty, and this will be taken to the data source. So the read operation will be performed to the data source from the filter 2. There will be some computation that will be carried out. This will be passed to the filter 1, and again it will be passed, again the final return data will be passed to the data sink. And we can see here, it is being carried out with a pull operation, and it will lastly end with here with the push operation to the data sink. The next scenario is a mixed push-pull pipeline with passive source and sink. So in this case, both the source and the sink are passive here. They are not implementing either push or pull, but the filters, whatever these are coming here, they are performing both mixed push and pull operation. So what happens? There will be a read from there will be a read from read between filter 2 and filter 1, and again there will be no data found. Again there will be a read performed by filter 1 and between the data source. Again they will be do a computation. It will be sent to the filter 2 from filter 1. It will be sent from filter 1 to filter 2, and again it will be returned to the data source. I hope you are getting how this push and pull will I'll be working. It's very simple. Both the data sink and data source are passive. So the filters are taking the role of push and pull. And initially, when it initiates, it finds it's empty because the data is in data source, and if the data is found from filter one. So again, they will do the computation from filter one to filter two, and finally it will be returned to the destination. And the third type is pipeline with active filters and synchronizing buffering pipes. Actually, this is the actual scenario which we will be using the pipes and filters. Because if there is no pipe and there is no synchronizations and buffer, it will not give you that much efficiency to this pipes and filter concepts. So what happens, what we'll see in here is there is a data source and data sink, right? There is a filters with implementing both push and pull, and there is a middle pipe with a buffer. So what happens again, the data will be read from filter 1. So there will be some computation that will be performed, and after computation and immediately no, even the filter 2 will also try to read the data from the buffer. But in this case, the data, the actually the filter one is actually doing the right operation, and again it finds is empty, and after it completing, it transfers the data to the uh, pipe. So after getting the right, it will do the some computation here, and we can see here that both F1 and F2 will be doing the computation parallel, as this buffering pipe provides synchronization concepts. We can see here both these are immediately after writing it to the pipe, it will read the data again, and it will start doing the computation, and it will write to the buffer. So this buffering pipe, it synchronizes, which makes us to achieve parallelism in this concept. The next thing is how we are gonna implement this pipes and filters. So implementation of pipes and filters is straightforward. Uh, the first thing is that we have to divide the functionality of the problem into number of processing steps. So we are nothing but we are just subdividing the different uh, functionality into different processing steps. We will define the type of format which will be traversing all the through pipes and filters. If suppose there is some uniform format, then it will be having high flexibility. But when we are using the uniform format, definitely we'll be having lower efficiency. And there can be even that we can introduce some transformation filter, where will be converting data from one format to another format. So but if you are having inform format, definitely will give us, it's a low efficiency. Then we have to determine how to implement each pipe connection. So we can either use a direct call or a separate pipe mechanism to implement the communication between the pipes and the filters. And we can design and implement the filters just as we discussed. It can be passive filter or active filter. As I said, the active filters will be having their own threads of control. They will be in a continuous loop. So whenever the data comes, they will implement push and pull. So, but the passive filter will be implemented whenever they are called, and they will not be usually having their own threads of control. And the pull activation is usually implemented with help of functions, and push is usually implemented through the help of procedures. But the other thing we have to keep in mind is design for a robust handling of errors. So as the filters, we usually don't have state information, and handling of error becomes difficult in this case, as they will be not having the records of the previous processing whatever have been happened. So this can be both a merit and a demerit to the pipes and filters. The other thing we have to think about this, the configure the pipes and filter systems, and we have to initiate the process. So we'll see a few of the benefits of the pipes and filters. The first thing is that reuse of filter elements. So what happens when the filters are simple, uh, we can implement it very easily, and transformations uh, can be typically encapsulated with fewer assumptions about the problem, and they are solving then filters that implement complex transformations. So what we are trying to get here is, when we are implementing a filter with a simple transformation, uh, they can be reused to another systems or applications of related systems. But when we are having a lot of complex transformation in the filters, then the reusability obviously becomes low. So if the transformations performed in a particular filter is low, then its reusability is high. If a transformation is performed in a particular filter is high, definitely its reusability will be reduced. So one of the added advantage for this pipes and filters is we can reuse the filters which has been already defined for a particular system, and it gives improved performance because pipes and filters process messages so as soon as they are arrived, because they process the do the computation incrementally as soon as they are we get it from a data source. The filters will not wait for the entire data to accumulate, so it helps us to uh, improve the performance. The other more benefits we can see is the efficiency by parallel processing. As we have seen in the previous diagram, the active filters run in a separate processes, or they will be having their own threads of controls, so they can work parallelly. They don't have to wait for the other threads, because they will be in their continuous own loop. So can help to increase the concept of parallelism. So, uh, what happens here? Intermediate files become unnecessary in case of some pipes and filters. Actually, even computing can be done without pipes by storing intermediate results in a file actually. But this approach, what it will do, it clutters directories and is error prone if we set up processing stages every time. So for such kinds of things we don't need some intermediate files, so to give a better performance. So these are a few benefits of the pipes and filters. Thank you.